So with that, let me just give introduction about the about VLSI, and then so we take a top-down approach. So we give introduction about the VLSI and the ASIC flow, and in the ASIC flow, where exactly the synthesis and the STA part comes in, and so that you have a clear understanding of synthesis and then STA role in the ASIC development. Okay, so what is VLSI? So VLSI is about very large scale integration of IC design and manufacturing. So basically it is the design and manufacturing or the fabrication of ASICs and the FPGAs. So on a semiconductor device. Okay, and what are the basic constituents or the basic building blocks of VLSI? Those are transistors. Okay, so in VLSI there are three categories. Okay, so one is full custom, and we also call it includes analog, right? It includes both analog and digital. That is full custom VLSI device design. Okay, so here right from the scratch we build everything, right? Means what? The transistors we design, the transistor characterization we make, and after that we use those transistors for the gates, right? The building blocks of the gates. Inside the gates, the logic gates, you have basic building blocks as transistors, and from gates further, right, you use these gates in order to model your hardware and to achieve a particular desired quality. Right from transistor till your right, what we call full custom, right from scratch. That's what it means. Okay, and the other category is where we also use this in ASIC, application specific integrated circuits. So ASIC, so we design a semiconductor device for a particular application. So what is the application? Finally, end product, which product it goes to, which electronic product this particular ASIC goes to. For example, you are designing the chip for mobile application processor, or the or a tablet, or a laptop, or any other electronic gadget, right? So now what is semi-custom here is, so you are using the already developed the gates. You will take those libraries, we call this library of gates. Already the transistor level you don't go, and you have optimized the transistors inbuilt into gates, and then you are directly picking the gates, okay, in order to build your device. So that is semi-custom. And the third category is FPGA. So the difference between ASIC and FPGA is it is field programmable gate arrays. I think many of you know this. This is one-time programmable, or it is one time you are manufacturing and you are building a product. And if the product doesn't work, or the chip doesn't work in a product, you will have to just throw that IC. But here there is a possibility of fixing the issues by reprogramming the logic within the device. That is field programmable gate arrays. So you will see pretty much these three kind of designs, the semiconductor designs in the industry. Okay, so in the other session where people have enrolled for right from the Verilog, so I also gave the industry overview, and also which are the companies who makes FPGAs. For example, Xilinx, Oildec, and Altera, which is part of Intel, right? These are the companies who focuses on designing and manufacturing of FPGAs, and also they provide specific tools for the FPGA design, like Xilinx. Some of you might have used Xilinx ISC, Xilinx Vivado, right? Those kind of tools. That is tools. See, basically the design, in order to realize the hardware, we use languages and tools. Okay, the languages are HDLs for designing, that is Verilog or VHDL. For verification, we use other languages, and basic languages like Verilog, VHDL you can use, but for advanced verification, you have to go for system Verilog, UVM methodology, right? And other even higher level languages like C for system level verification, you know, we can use. Okay, and other part is tools. So EDA, you know, it is electronic design automation. Okay, so that's the industry, and EDA companies like Cadence, like other mentioned, you know, Mentor Graphics and Synopsys. These are the three leading top three EDA tool companies who build tools for semiconductor design, you know, hand in hand. Okay, so any companies you take, you know, there's you know, Intel, Qualcomm, Broadcom, all these semicon companies, they are largely dependent or using the tools from these EDA companies in order to build the semiconductor designs. Okay, so that is about the EDA tools. Okay, so now whatever I mentioned, Xilinx, Vivado, or ISC, coming from the Xilinx, and for ASIC development, you can use any of these tools from these three companies, generic, right? Like, you know, Cadence for simulation, we use NCSIM. For synthesis, you will learn Genus, and for timing analysis, you will learn Tempus. This is all from Cadence. Similar to Cadence tools, other companies, Mentor Graphics also gives equivalent tools, and similarly ICC coming from Synopsys for the physical design, right? Per prime time for timing analysis from Synopsys. So like that, all these EDA companies will provide tools in order to achieve specific goal in the overall ASIC flow. Okay, so we will learn what are the steps in building the ASIC, and where is our synthesis fits in. Okay, so that is the overview of VLSI. Okay. So a little bit more about full custom or the analog flow. Okay, you start with the specification, right? What is, see, basically in the full custom, you are optimizing right from the transistor level, the small component, right, and taking it to the bigger designs. And architecture, and what is that, you know, you are optimizing? It is mainly about, you know, power, performance, and the area what each transistor can take on a semiconductor device. And architecture, right, and basically at a high level, you know, goal setting at the architecture level. And you get into the circuit level description. Okay, the circuit level description, and you also verify, right, or all the characterization you do. And so you can look at the theory what you have studied, the small signal modeling, or HIE, FIE, what is the gain of the transistor, what is the response time, right, and all those characterization you get into at the basic level. Okay, so, and finally you are getting into the layout, and that's the physical design part of it. And so it is the finally the fabrication part of it. So it is a very you know, high level bird's eye view of full custom flow, which shown here. Okay, and this is including, so full custom execution. Okay, so you will see in the ASIC what is the difference. Okay, so FPGA flow. Okay, so you will do the design and verification using any HDL. Okay, Verilog, and you synthesize. So your synthesis will be done in the FPGA flow by taking it to a particular FPGA where you want to realize this design. For example, now you want to implement the design using Xilinx FPGA. So then you do the synthesis using Xilinx tool. Okay, and you do the implementation part of it. So basically FPGA, if you know the basics of it, it is already having the logic blocks inside. Okay, and you are fitting this design into your logic blocks and realizing the functionality. And the fitting means what? Now you're synthesizing, and also you are implementation stage, you're doing the fitment and the timing analysis, right? All these you do for that particular to fit this design into that particular FPGA, and you do the timing analysis. Means all this, you know, now the synchronous circuit, what timing analysis in STI, you will learn lot of it actually. And here also you do in FPGA. Okay, and finally you are going to program the, you generate the bit file using your Xilinx tool or any FPGA tool where you are targeting the design to be fitted, and that configuration file you are going to program it to your FPGA board, and that so that the FPGA can function as you have designed. So this is in nutshell about FPGA flow. So throughout you do couple of analysis, that is power analysis you do, and your simulation you debug for the functionality whether it is working correctly, and also the timing analysis, the timing closure means whatever your budget. So to give a simple example, you have designed this device to work in a particular frequency, right? Let us to work in say 100 megahertz. So now within 100 megahertz budget, whether the circuit is working properly, right? So those things, you know, what are the intricacies, how we make sure at the flip-flop level, gate level, what are the kind of delays, right, will come into picture. That is the you know, things, those are the things which you will learn more in detail in upcoming sessions. So this is about FPGA flow. Okay, now the third part is the semi-custom, the ASIC part of it, right? So ASIC is designed for a specific application. See, in FPGAs could be generic, right? And in some cases, they will also be industry aligned. Okay, so where they will you know provide FPGAs with some IPs embedded within the FPGA, so that you know you can you can use that. Let us say PCI Express or generic processor core like ARM Cortex, right? So now any device, any application, you need a generic processor, right? So that way FPGA companies also, you know, at times if you go for a higher configuration, right, and they will, and which are the parts or which are the FPGA devices which are having those cores inbuilt, right? So what I'm trying to say, in FPGA also, depending on your application, you can choose FPGAs. Okay, that's one part. And apart from that, rest of them, it is blank, you know, blank logic blocks will be given to you, and they will tell this particular FPGA is having this many logic blocks, and then based on your design complexity, you can pick and choose and then build or embed your design into the FPGA. Here, ASIC is your developing or designing for a specific application. Okay, so there will be specific analog design requirements. Okay, so and you are building complete SoC, right, system on chip, and then it has to address the SoC design challenges. Okay, so it could be about meeting the power numbers and the performance and the area, right? Lot of other challenges what you go through when you are building the SoC. Okay, and of course, you know, market introduction growth and the maturity, it comes more from the marketing point of view, whether your SoC is on par with the competition, what technology it uses, and you know, and what are the features it supports, right? All those comes into picture in the market introduction growth and maturity. Performance, like I said, performance, bandwidth, performance, speed, all these you can use interchangeably, right? It is about how fast I can get the things processed. That is about performance. Okay, and size and packaging. So you might have seen, to give an example, so when Intel introduced mobile chips for mobile devices, so you might have come across or you know seen that they went with one company, and then the model what I remember is Zolo. Okay, for India market they released actually. So that is Intel chip inside the mobile device. And so that one, so there were reports saying that, you know, when you take ARM processor inside and then that one mobile device and the Zolo phone, so they're comparing the boot up time. Okay, so you're switching on both the devices, which is booting fast, right? Booting means initial, you know, it is the initial configurations and also the booting and loading the operating system and then making it ready for you to use, right? So that way what they were doing at that time is to push the chip and also the devices to the market. Okay, so at times, right, and they also proved, okay, this is faster than the exit. So basically I'm giving an example for the performance, what performance means. Okay, the size and the packaging, right? So that is the other part, what kind of packaging they should go, size, right? And packaging, whether you go for different packaging, like you might have studied small ICs, some dip package, and then TSOP package, right? And now BGA is ball grid array. So that is what is, recently they use the packaging part of it. Things will become critical, right? So for the ASIC, and all can be customized for a particular device. So that is where ASIC comes into picture. So why ASIC? So these are all the reasons where you can have the flexibility in order to address all these challenges actually separately. But FPGAs, you are given a device and then you design and then you fit in your logic inside the FPGA, right? So that's where ASIC is very popular when you are building for a particular application. Okay, so how do you go about designing an ASIC? So you collect requirements, right? What requirement means initially, what is the end, what is that this chip has to do, right? And then you come up with the high level block diagram, that is architecture stage. And next is RTL design. You use an HDL, means hardware description language, like Verilog, and then VHDL, and then you code the architecture, the blocks, what you have, you are intending to design. And RTL verification. Now you have to verify the functionality. Little bit I touch upon all these topics separately, even these blocks in upcoming slides. So I'm just the flow I am explaining: design, verification. Now, so the design, once it is you are taking the design to the synthesis process. So this is the process which we'll be explaining more. Okay, and this is logic equivalence check. Once you synthesize, so basically the Verilog code is converted to gates, and then you will have to check that the gates what you have got through the synthesis process is equivalent to the RTL what you have written, that is LEC, logic equivalence check. And DFT process, that is designed for testability process. Okay, after synthesis, there are steps which where we will include some structures in order to test the chip once the chip is out. Okay, so that is after synthesis process, like scan, insertion, ATPG, all this will come in DFT process. And pre-layout STA, this is where before we take and then do the layout, we do the static timing analysis. Okay, so that is pre-layout STA. And now we do the physical design part, which is layout, floor plan, power plan, placement, routing. All this we do in the physical design process. And after that, we do the physical verification. Okay, and so we perform the post layout STA. After layout, see, STA is very critical step in the ASIC process. It is performed at different stages, STA and the verification, so that we are meeting the functionality and desired functionality, and also we are meeting the timing aspects. And DFM, design for manufacturability. Okay, and the other a couple of steps are there, and this we will explain in the upcoming slides. Finally, it is GDS2, okay, the graphic design system format. This is the one which we will, which the companies, the design houses send it to the foundry. Okay, foundry means, okay, who can manufacture the chip, who can fabricate the chip. The fabrication houses are companies like TSMC, Global Foundries, and Intel, for that matter. These are all the companies who have foundries of their own, who can design and also manufacture. Okay. Otherwise, some companies like, Broadcom, Qualcomm, these kind of companies, they are fabless companies. They don't have the manufacturing unit with themselves, and they design, and then they give this Gerber or the GDS2 format. It's a graphic image. It's not readable format. Okay, only the machines can read. So this part will be shifted to the such companies. Okay. So I'm hearing some sound. So are you people just getting the flow? Is it going fine? Just I'm giving the bird's eye view, the high level picture of it. Is it going fine? So you can use the chart window. Okay. Okay. So that is about ASIC. So far we discussed about the three things, the semi-custom and the full custom and the FPGA. What is the difference and what are the flows? See, one more thing, I think, adding to what Damodar said initially. So we'll be covering certain concepts in the theory sessions, and then we will be taking to the tools and we'll be applying there. So at times, I know people will be restless. Okay, show me the tool and show me the things how I can do with the tool, right? And without knowing the theory and the concepts, you cannot utilize the tools and the languages effectively. So I know you are more into theory sessions actually. Well, you're studying in engineering, right? And you wanted to learn more about the hands-on. So we will come to that, right, as required. But understand the overall picture here. So the next is the chip architecture. So each of these stage, little bit, we give an introduction and then we move on to synthesis per se. So at the right, so there are various IPs, various modules instantiated in the system. So if you look at, so as you this particular ASIC, so it has a application processor, and it has, say, display interface, it has Wi-Fi or Bluetooth interface, and GPS, USB, and a micro SD card interface. So all that, if you look at in your mobile, audio interface, mic, speakers. So the end product, right, whatever you would like to have, should be supported by the chip what you are designing for that particular application. So the VLSI is all about, right, building these IPs, integrating, and then making this chip. This complete thing is called is a chip, or the SoC, system on chip. Okay, the system on chip also, to just give, you're putting a complete system on one particular device. One is the hardware design, other is you have memory, you are putting embedded software into it, right? In your mobile already you have Android, or if you have iPhone, so the Apple OS is running in the device itself. So that's where the complete system on chip, right? That is where the word SoC has come into picture. Okay, so the architecture level, based on what application you are designing for, you are taking this and building each of these IPs, and they will define what speed USB should operate, right? And how much SD card it should support, right? What is the DDR size, right? For example, now when you go and then buy a mobile, you'll ask for 64 GB RAM you want to have. So when you say that, you are intending to have a very fast device, right? So nowadays 256 GB RAMs are available, and for flash memory maybe 256. So this is for storage. This is for when it is running, it uses the temporary memory, that is DDR, the RAM. This is what speeds up your your mobile or any device performance. Okay. Y means when operating system is executing, when you're running the software, how much free space or the heap memory they call, okay, heap memory. So where it is computing, it is storing temporarily, and then again retrieving back. So this is the same concept like cache memory what you have in desktops and the laptop. Okay, so so that's how I am highlighting about what kind of decisions, what kind of things will be considered at the architecture stage. So all these chip architect will decide about, so what voltage each of these blocks should work, right, or can work. All these will be given and defined in the architecture specification. Okay, and there is PMIC audio codec, and PMIC means power management IC. So see, anytime this is very critical, the power management concept. So because at times a device will get heated, and also it will consume more power, and then the battery will get exhausted very fast, right? All these things, right? So will be effectively managed by power management IC. And so this also manages, for example, when you are not using the chip, when you are not using a particular interface, let us say the display interface. Now you have all kept your mobile side and you're taking from the laptop, and your display screen is off, right? What it means is the display screen, the display controller sending the data to to the display, that engine is switched off, right? That is in stand mode, right? The moment you click this home button, so at least one the basic things will appear, and then you can further go. So basically this home button pressing will go as an interrupt to wake up the system. So all those kind of things are managed by power management IC. You will see in all these synthesis classes power reports, right? You analyze power reports. What is the power consumed, right? So power management is also is an important aspect in today's this VLSI world. Okay, so like this, all this camera interface, what should be the megapixel? Is it a low cost mobile? Just maybe 4 megapixel or 10 megapixel you give. If it's a high-end smartphone, right, you can go for more than now megapixel, right? All that today what you see in the latest mobile phones, right? So all these kind of things will be defined at the architecture stage. Okay, and so the critical things are functionality or the application, what application it is, and performance, power, and the area. So now, is this going to be used more a handheld device? It's going to be most of the time residing in your pocket, in consumer pocket, or they will be in consumer bag, right? So that way, if it is laptop, if it is desktop, or if it is some industrial application, for example, now when you are designing some chip or the ASIC for a UPS, right? So in UPS, really whether the space is a constraint there, right? So like that, depending on where it goes, or in an industry, so the area may not be a constraint, and so in those kind of cases it is not so critical. But handheld devices, definitely the area is critical. So schedule, time to market is very important, right? How fast you can bring the device into the market in this competitive world, right? So all this will be considered, and the blocks and the interfaces are decided, and in the chip architecture specification, they will also include the configuration registers for all of these blocks, input outputs and the clock and reset and timing, everything, what frequency it has to work and how many IO pins are there, right? All these things will be defined, and of course it will be reviewed, and it's an iterative process. So these are the things which will be done in the chip architecture stage. Okay. So the next is the design itself. I call that as a micro design. So now take a particular block. Let us say there I mentioned about this. This is called IP or a module or a block. See, today's world, right? It is a collaborative effort. One company, will not build the whole thing in practical, right? In one of the project what I worked, see, there used to be more than 25 IPs, right, coming from close to 10 companies. What the end product building company was using for. So that's why they call IPs. That's why individual blocks are IPs. Why means why IP? It's an intellectual property of that particular company, and they are giving it or licensing it into a product builder. Okay. So now you take this. Now one block, how do I design? Right. You go to the intricacies of that. Let us say I2C interface, I2C, I2S interface is used for sound. Okay. So I2S is for sound. So now you will have multiple blocks within register block and the audio processing, and so those kind of things you will define more at a hardware level. Okay, so you're seeing the synchronizer, analog to analog, not analog, asynchronous signal. When you are taking it to the synchronous world, you will synchronize, and then you will, if it is serial serial data, you are converting into parallel. That's where deserializer is used, right? And when you are sending, it's a serial, let us say I2C or I2S, these are serial interfaces. Means what? One bit at a time. Okay, so then internal processing within the chip you will do with parallel processing with 8-bit or 32-bit or whatever, right? So all those things, when you're sending it out, you may be serializing. So now and then this BIST DFT and the multiplexer and the FIFO and the flip-flop. So what here I'm trying to say is you will have to split up your functionality to the gate level or to the block level, the micro block level, so that it is easy for you to code in Verilog, code in any HDL. Even you can use VHDL also, but predominantly Verilog is being used mainly because of US influence. So Europe uses more of VHDL, and now also legacy designs in our space you will see in VHDL. But otherwise, Verilog is mostly used by many companies today. So now if you do this at this is what real design. So never ever think that VLSI design is about writing software. No, it is, you have to have a clear picture of what hardware you are implementing, what hardware you are constructing, what are now hardware means. Now what are the building blocks? Now the synchronous combinatorial circuits, sequential circuits, right? And you say this multiplexer, it's combinatorial, sequential, synchronizer, flip-flops, memories. So this knowledge of these basic components is very important. Using those you build, and then now use, that is the next step, take the help of the Verilog or VHDL to write RTL. What is RTL? It is register transfer logic. Okay, what you are trying to do, you are overall in the previous diagram, it is all you are taking the data, and then from this block to this block you are transferring, right? Of course you are doing some processing inside, okay, and then to the multiplexer, to the FIFO, and then finally, right? So all that what you are doing here is the transfer, right? Is the data movement. So and register. What is register? So the basic register can be realized like 1-bit memory. Okay, 1-bit memory. It could be any flip-flop can represent a register. Okay, so of course you will use 8-bit, 32-bit, or 64-bit today's this one. So that way you will use that many registers. So that's how the name here. And it's a design abstraction which models the synchronous digital circuit. So that's where the moment you say register, it is synchronous, we say. Okay, basically synchronous and asynchronous. The synchronous digital circuits are designed with respect to taking the reference as the clock. The data movement data movement happens with a reference clock, right? So which is running at a specific frequency. Okay, asynchronous means it doesn't have any. You may have enables and disables, but the period or the on duration and the off duration of an asynchronous signal is not predetermined, right? So and it is very difficult to control also in the design, and also it leads to multiple issues in terms of the timing, in terms of noise, like glitches, right? Because it's unpredictable. So a lot of issues with the asynchronous design. So that's where most of the time or all the time we go for synchronous digital circuit. Okay. So like I told, it is the movement of data from register to register, and further it is flow of digital signals between hardware registers with certain logic operations. So here when you use hardware, always the things comes to our mind is some board, right? Digital board, right? So now in this context, right, your chip, within the chip, what you are doing, right, the transistor level, the memory level, the flip-flop level, that is what we say hardware. Okay. So the synchronous circuit consists of two types of element, that is sequential and combinatorial. Okay. So I think definitely you all are aware of what is sequential and what is combinatorial. So combinatorial circuits, right, are outputs are depending on inputs, and there is no memory in it. And registers output is not only depend on the inputs but also on the feedback path or the memory, right, which is stored, right? So further, what is register? Register synchronize the circuit operation to the edges of the clock signal, okay, and are only elements in the circuit that have memory properties. So like I said, performs all logic functions. Examples for the combinatorial circuits, all your gates, AND gate, OR gate, NOR gate, NOT gate, those are all forms the basic combinatorial circuits. Your multiplexer, your demultiplexer, your encoder, decoders, all these forms the combinatorial circuits. Sequential circuits, mainly your flip-flops, your memories, right? So these forms the sequential circuits. So your ASIC design, your RTL will have both registers and the gates. In other words, both combinational and sequential circuits. So the term refers to the fact that RTL focuses on register transfer logic. That's why this thing. Languages, like I said, VHDL and Verilog. Tools, this also I mentioned. Now, this incisive enterprise simulator from Cadence, VCS from Synopsys, QuestaSim. So this is for the front end, for the simulation, for designing and simulating, we use from Cadence. Any one of these is fine. So normally all will support whatever code you write in VHDL or Verilog for compiling, for simulating. Okay, so these are language agnostic. These are language agnostic. Otherwise, we can also say Verilog is tool agnostic. Anybody who says I support Verilog compilation should take, because Verilog itself is a IEEE standard. So you will be using the prescribed language syntax, and then it should work, and all these people should be able to support the compilation and the simulation. So just I take one example here. It seems very simple. How do you write a Verilog code for one flip-flop with with a combinatorial part which is NOT gate? It is a flip-flop, is a sequential circuit, and there is a reset, and there is the feedback from output to this one. So Verilog goes with a module, right? The whole inputs and outputs you will define in module, and you give a direction, which is input, which is output, and internally you define wire or reg depending on wire means in order to define combinatorial, and reg means in order to define the sequential. And within the always block, you have written at passage of the clock. Anytime clock changes or reset changes, you go, and then this is procedural. Okay, so this is procedural. So anytime the always and assign, these are concurrent. Concurrent means this and this whole thing will be executing at the same time, but within always block it is procedural. Means what? One after the other. So first it will check if reset is there, then it then Q will be 0, else then Q is assigned with the D, right? So then finally this Q is output, and then D is what, right? D, it's a wire, and then this itself will be not of Q. Okay, so this D is not of Q. Okay, so basically here just I have given an example of code. I know you might have seen still complex Verilog HDL codes, and those are the things which we will take it for synthesizing. Now, if you synthesize this code, finally you should get one NOT gate and one flip-flop. Okay, so these are also called standard cells. We talk about this. NOT gate is a standard cell, and this flip-flop is standard cell. Okay, so that is about RTL. Now we discussed about chip architecture. Next is the design, and you are verifying. So you need to verify the functionality, right? So basically by applying stimulus through the test bench, test vectors are applied at inputs, outputs are captured and checked for the correct behavior. And complex designs today uses system Verilog and then UVM kind of languages and methodologies for verification. Okay, so you can check basic cases and the corner cases, all this. So this is in order to represent or show diagrammatically test vectors, and you drive from the component, right, the test bench component. This is the design, and basically reset, clock, right, you are driving from here, and output Q you are collecting and then checking that, okay, what is the functionality, right? So this is basically what you do in the verification part of it. Okay, of course you will use the waveform viewer for debugging the functionality. Okay, so you will look into the waveforms. Okay, with respect to the clock, I gave this data, and then what it is supposed to come, right? All this functionality you will check. So this is what you do in the RTL simulation, right, in order to verify the functionality.
Oh, yeah.
Yeah, go ahead and take it through, in the same pace. Yeah.
Yeah. So thank you for the introduction of the front-end design. So I'll be walking you through the process of back-end design flow. So the first step in back-end design is a logic synthesis, and where we convert the RTL code, whatever is designed, into a gate format. So at this particular stage, we convert the RTL code into a gate level netlist so that it can be physically implemented on a chip, or like it will be going for a fabrication. So it has to have some physical implementation. That is the reason we directly can't dump the RTL in the same way on a chip. We need to convert that particular RTL into some physical parameters. So that physical parameters are nothing but the gates. So at this particular stage of logic synthesis, we convert the RTL code into a gate format. So parallelly, when this stage of synthesis is happening, we have a stage called LEC, that is nothing but logic equivalence checking. So once the gate level netlist is converted, so it has converted the gate level netlist according to the RTL code we have coded or not. So at this particular stage, it checks the functionality of the RTL. Whatever we have coded, it has properly converted them into gates or not. So this is the second stage, or the parallel stage, which is comprising in the backend flow. Both are the first steps of the backend flow. So next stage is the DFT stage, that is designed for testability. So at this particular stage, we give some testing inputs or in the form of gates in the circuit or in the module, to test or to control and to observe the logic whatever we have written is functioning properly or not. So I'll discuss more about this DFT when I move on to the later slides, where I have described each and every stage elaboratively. So next stage after DFT is pre-layout STA. So pre-layout STA, we do the timing analysis. So till front end, we are only bothered about the functionality. Nowhere we are checking the timing, not like we are giving any timing inputs to the circuit. No, we are not checking any timing information of the circuit. So from this stage, like from pre-layout STA stage, we give some timing input to the tools, and we generate some timing reports, and we do the analysis of the circuit. So pre-layout STA is nothing but pre-layout static timing analysis. At this particular stage, we perform timing analysis only for the gate level netlist that is generated from the logical synthesis. So next stage is physical design. Now, whatever gate level netlist I have generated at the logical synthesis stage, that need to be implemented physically in a particular area with some interconnections, with some like power parameters, with some logic, extra logic, like the well tabs or end caps, that is nothing but some physical logic. So we need to implement the gate level netlist of the synthesis in a physical format. So that particular stage where we are implementing the gate level netlist in physical format is called as physical design. And next is post layout STA. So in the pre-layout stage, we are just doing the timing analysis of the gate level netlist that we have got from logical synthesis. So there, the connectivity of the logical gates will be there. But at that pre-layout STA stage, it's just an estimation connectivity of the gates. But when you come to post-layout STA stage, the connectivity, whatever you have given or implemented in the physical design stage, will be the actual connectivity of the circuit. So when you are implementing it actually, I mean to say physically in the physical design, so the delay values and the timing values of the logic gates will be changing. So in the post layout static timing analysis stage, you check the timing of the circuit with the interconnectivity information, that is nothing but the actual interconnectivity information. So once this interconnectivity timing analysis is done, we'll enter into physical verification stage, where we perform the checks related to physical design, and what are those checks and all, we'll be seeing them in the later slides. So once we do the timing analysis, we need to check the physical connectivity, how it has done the physical implementation. So at whatever checks we are performing once physical design is done is called physical verification. So design for manufacturability. Now, whatever you have implemented the logic at the physical design stage, or the tool have implemented, or the routing or the connectivity of the circuit has been done, that is proper or not. Will it be suitable for me to take for the manufacturing process or not? So at this stage, we just do some minimal checks for like for rechecking the circuit, will it be okay for me to to send the circuit for the manufacturing? So at the DFM stage, we mainly do some minimal checks of manufacturability. So once this is done, now the complete circuit is verified without errors, and a format of graphical design schematic or graphical data schematic is created, and that is sent to the fabrication. So this is a physical format. Finally, once the complete backend flow is implemented, we'll be giving it to the fabrication stage. So this is just the introduction of the backend flow. Now let us get into each and every stage elaborately. So the first stage, as I told you, is synthesis. So basically, it converts the RTL design into optimized gate level netlist, and from here on, like from the backend flow, it is mainly tool dependent. That means like most of the process will be done by the tool itself. So as a user or as a backend engineer, you just need to give some inputs that is required by the tool, and check the reports, like whatever tool has generated according to the inputs what we have given properly or not. So from the backend process, it is mainly a tool oriented design implementation. Now, once the process is converted into gate level netlist, so why it is converted into gate level netlist is, so as I told you, RTL, whatever it is verified functionally, cannot be directly fabricated because it's some coding language, it's some description language. We need to convert them into some physical concept, physical blocks. So that blocks are nothing but the logic gates, and now the RTL is converted into some technology dependent format, into a logic blocks. That logic blocks are nothing but the logic gates, the simple gates like AND, OR, XOR, and XNOR, and any combinational gates like decoders, encoders, adders, and multipliers. So that and all will be implemented on the chip. So to make it fabricate, we need to convert that RTL code into gate level netlist. So this is how the gate level netlist looks, and the schematic or the gate level implementation of that particular gate level netlist. This is just an example. Okay. So the next step, once we do synthesis.
Ma'am, I have a doubt.
Yeah.
Ma'am, how to read the gate level netlist that I didn't understand?
How to? Can you repeat your
How to
question?
read the gate level?
How to read? So we are not reading any gate level netlist. We are taking an input as an RTL design, and the tool is generating a gate level netlist. So we are not manually reading the gate level netlist. We are reading an RTL design.
No, so
Is it
at the
clear?
layer, how to understand it?
So like once I implement it in the tool, you might get to know the procedure of how it is converting into gate level netlist. So there are some particular stages how it is gonna convert. So I'll be discussing at that stage.
Okay, just to add on, Shravanti, for this question, see, if you are looking at the screen, there is DFM SRX2 in the netlist block. Are you seeing this?
Yes, sir.
Okay. Now, in Verilog, you might have known already that you are instantiating a component, right? When you have multiple blocks in the top level, even in the architecture, whatever I explained, there will be multiple blocks, and these blocks will be instantiated in the top level. So in the netlist, right here, you will see all the Verilog code has been translated into gates. Okay, gates / standard cells. So the standard cells we say there could be combinatorial circuits and also sequential circuits like flip-flop. Now here, if you look at with that understanding, so first component, let us say NAR2BX1. This is the standard cell, and you have in this one you have taken an instance of it. This is the instance name, okay? And you look at in this bracket, inside this. Now, what is this NAR2BX1? It is 2 input and then 1 output, I think. So now, what are those 2 inputs? .an is connected to read mux byte 0 register bit 3, comma, right? That is one input. Second input is .b. See, .an, .b are the input ports of this NAR2BX1 gate. And .y means an and then b are the inputs, but here I am connecting the ports. That's where I'm using dot here. Okay, I am instantiating and connecting, and .y means, so the y port is connected to what? PR data bit 3. Okay, this is how you can read, to understand. For example, now you see read mux byte 0 reg 3 will be coming from one flip-flop. That one is connected to this input. Okay, unfortunately in the Google Meet there is no whiteboard this thing. So otherwise we would have written and showed. So that is how. So here in the same way, DFF, okay, D flip-flop, right? That instance is baud updated reg, and .rn is reset pin, and SN and the clock. So the ports of this DFF are RN, SN, clock, T, Q, right, and QN. So this is reset and then this is set, and clock pin D input, Q is Q, that is a positive, right, and QN is Q bar. So this is how you can read for your understanding. Is that clear?
Yes, sir. This is what I wanted to know.
Okay. Okay. Fine.
What is the file extension for Netlist, sir?
File extension, it is Verilog Netlist or VHDL Netlist. So here, whatever the synthesis tool will dump out, that will be .v. That is where whatever you do in VLSI, Verilog language understanding is a must. .v. Okay.
Even for Netlist also .v only?
Yes.
Thank you, sir.
Yeah.
Okay.
Then how to distinguish whether it is a Verilog file or Netlist file?
So looking at the contents, okay, see, finally, you are, let us say you are feeding a Netlist file to the physical design process, right? So physical design tool, right, can only read the Netlist, not the Verilog syntax. Like whatever you write, like always, art, poset, all these, right? It will not. Then anyway, you will get error anyway. So the mapping of ASIC and then FPGA. What is the difference? Can you elaborate on this question, please, Anu? What is that you wanted to know?
Pardon? My name is
No,
Radhika.
someone. Yeah, what is that you wanted to know? Can you be more clear about your question? Explain the difference between technology mapping of ASIC. What is that?
I'm not asking on technology mapping, sir. I would like to know the difference between Netlist file and Verilog file. What is the extension I want to know?
Yeah, that I cleared, right? Is that clear? Whatever I said.
Yeah, but after opening the file only we can understand that.
Yes. The content. Otherwise, both the files will be having top level module. Inside the module, what will be there in the Netlist file is the Netlist, and the top level module inputs, outputs, and the Netlist.
Hello.
Within the content, and in the other one,
hello,
the Verilog syntax.
Hello, sir.
Yeah. Yes, go ahead. I am not able to hear.
Okay, can you hear me now?
Yes, go ahead.
Sir, actually, what is the difference in the technology mapping? So if you are converting to actually standard cells. So how it is different in what is the difference in ASIC implementation and FPGA implementation?
Okay. Now the standard cells, if you look at in the FPGA flow, how we use, right? See, we are only utilizing the Verilog design or Verilog or VHDL design, and the rest all will be taken care by the Xilinx or Altera tool in terms of the, for example, FPGA itself. They will say this particular FPGA is for this technology node. So all the logic blocks which are already inside the FPGA, it is fixed for a particular technology. Okay, and in the ASIC flow, what happens now when you are designing, you have designed Verilog, and then you can take that to whether it is a 16 nanometer technology or 10 nanometer technology. You can go and experiment whether you can still do that with the lower technology nodes. Okay, that way the standard cells will be provided by the manufacturer like TSMC or whoever foundries provides the standard cell libraries. So here it will all be going to the particular technology what this FPGA is already designed for. FPGA, they will all the technology node is already fixed by the FPGA vendor, FPGA company. And the synthesis also will be done within the tool, and you are giving the specific this thing from the FPGA company only. Okay, so that's the FPGA and the ASIC. Okay, so you can move forward, Shravanti.
Okay. So yeah, once it is converted into a gate level netlist format or a gate format, we need to do one specific check called as logic equivalence check. So what is logic equivalence check is basically you have designed some RTL. So it has to convert some into particular gate. Like if you have written some AND logic, due to some issues, it is not picking the proper AND gate. So in that place of AND gate, it is picking some other gate like OR gate, or it might be some other 2-input gate. So that is it will lead to a functionality issues. So to check that particular kind of issues, like the mapping of the gates while conversion of the gates in the process of synthesis is done properly or not, we particularly do at this stage. So logic equivalence, we are comparing the RTL code and the netlist that is generated after synthesis parallelly, line by line, and we are checking any mapping of the gates is done wrongly. So it is also again a tool oriented thing. So in the tool we load the two files parallelly, and wherever the logic is not mapping, that means wherever it has picked a wrong gate, it will show us in a report. And again we do the process of synthesis by some modifications of RTL, so that it will convert that particular RTL into the gate which we wanted. So here the netlist and RTL comparison is basically done in this process. So this is about LEC. So next is design for testability. So this is the testing process of the circuit, where you basically check the observability and controllabilities of the circuit. So what is observability is, so if I take an AND gate, if I give an input 0 0, I need to get an output 0. So if now as I told, like as sir discussed also, ASIC is basically for the larger circuitaries. So now in that larger circuitaries, if a simple logic like AND gate is projecting such kind of test vector issues, I mean to say, it has to project a value of 0 when it is given an input 0 0, it has to project an output of 0. So it is not happening at a simple logic gate in the complete circuitry. So once it is implemented, or once it is taken to the fabrication, it will be difficult for the designer to detect where the error is going, or where the fault is going in my circuitry, so that my functionality or my output is varying. So at design for testability stage, basically we send some scan cells, or we send some test logic as an input to the netlist, and we test the functionality of that cells at each and every node to node point and point to point of simple complex cells, so that the vectors whatever we are giving at each and every input of the gates is tested properly, and we are getting a finalized output. That is nothing but the output we are expecting. So design for testability is basically we are checking for the functionality of the complete circuitry end to end, point to point, by giving some test vectors or the test logic or some patterns. So this is the elaborative description of design for testability stage. So this is basically done because once the circuit is implemented completely, we can't find out the error or the fault in a simple gate, like the picking a gate and checking it is impossible. So in the before stages itself, if we do this, so that our chip can be fabricated without any faults. So once this is done, we will enter into a stage called static timing analysis. So till now, like till the DFT stage, we are only we are only back of functionality, and we have not given any timing inputs to check the timing. So why timing is important is, so let us take an example so of mobile phone. Like if I on the power button, so if it is on after 5 minutes, so it is not okay for me. It has to on at that particular instant of time. So that performance is basically tested in the stage of static timing analysis at the circuitry. So at this stage we give some inputs of timing and do some timing analysis. Basically two types of timing analysis: one is setup timing and the other is hold timing. So basically, as I told you before also, this is done in two stages. One is pre-layout STA, that is once after the synthesis is completed, and one is post-layout STA, that is once after the complete physical design flow is done. So the difference between pre-layout STA and post-layout STA is, so in the pre-layout STA, we just do the timing analysis on the netlist that we have got from the synthesis. So you got a gate level netlist and you are just estimating it with some timing inputs, and you are checking the timing reports. So here itself, it is failing very badly. That means it is showing a huge number of violations at this particular stage itself. So we can't move it forward. So that is the reason we check it in the pre-layout stage also, so that in the later stages, it should not show me any difficulty. So this is also one added advantage where we can know the timing violations in the before stage itself, so that we can reconstruct the circuit, or we can reconstruct the RTL in such kind of format, or we can reconstruct the timing inputs that we are giving to the tool. So it will be an easy process for us to estimate the violations. So that is the reason they perform pre-layout STA. Now here, as I told you, the delay values will not be accurate. It is just an estimation values that the tool is generating, because it is not actually implemented. So it will be implemented once the physical design process it will start. So and they may be treated as 0 also, so no input vectors are required. So as of now I am not giving any input vectors like any physical parameters so that I can estimate the delay values. I am just giving some timing input where it is giving me the estimation output of delay values. So when you go to post layout STA stage, that means your complete circuitry is physically implemented. Now with the help of the timing inputs we give at this particular stage, it will be able to to detect the actual delay values of the cells of the interconnects of the particular circuit. So here we are giving some extra database, that is routing database, as one more input. So this is again done in the tool. So this is also a tool oriented process. The tool we use for static timing analysis in Cadence is basically Tempest, and in Synopsys it is DC compiler. So this is about pre-layout STA and post-layout STA. So like one of you were asking the question regarding this pre-layout STA and post-layout STA. So is it clear now?
Yes, ma'am, it's clear now.
Okay, thank you. So once the timing analysis is done, now my timing violations are at a minimal range and I can move forward with my implementation of the design in a physical format. So I will start off with a stage called physical design. So in the physical design, the floor planning is the first stage. That means again it is segregated into multiple steps. So in the physical design stage, the first step is floor planning. So when you get a module, I mean to say when you get an RTL and you are converting it into gates, in how much area that gates will be placed and how much area it has to contribute, that module has to contribute in the complete IC, I should know, right? So that particular area estimation and the implementation of some files will be done in the floor planning stage. So once the floor planning is done, next comes the partitioning. So partitioning is basically, now you have some different groups of logic when you consider IC. That means you'll be having an ALU operated circuit, and you'll be having some power related circuit, and you'll be having some I mean to say that the internal circuitries like the interfaces, as sir discussed, if for the processor it is I2C and I2S. So that is partition, I mean to say that group of logic is separated at this particular stage. So once the area estimation of the complete logic is defined, it is divided or it is splitted according to the functionality logic it has converted into gates. Now obviously once logic has to be implemented, or once the circuitry have to be in the process of running, we need some power. So to on the circuit, we give some power planning, and we do some power planning with the circuitry we have, and that stage is nothing but power planning stage. So placement is nothing but, so in the floor planning you have estimated an area. So like this much area my gates are gonna apply gonna occupy the area in the later stage. So in the placement stage, whatever area we have estimated in the floor planning stage, we just dump the cells whatever we have planned in the floor planning stage. So the gates which are coming from the gate level netlist are dumped at this particular stage. So placement is just an automation done by the tool where the gate level netlist gates are dumped into the area that we have done in the floor planning. So once you get a gate level netlist, mostly the cells will be comprised of the sequential cells, because obviously any circuitry or any module will be having a memory logic itself, and to implement that memories we need obviously flip-flops. So most of the IC or the integrated circuits will be comprised of the sequential cells itself. So at the clock tree synthesis stage, the gate level netlist we have placed in the placement cell, I mean to say the placement stage, we just give clock to each and every sequential component that is present in my placement stage or that has come from the gate level netlist. So clock tree synthesis is a stage where we are just propagating the clocks to each and every sequential cell that I have got from the gate level netlist. So now I have done the placement of cells. I have just propagated the clock. I did not do any interconnects between the cells. So I just placed the cells, I gave the clock propagation, and I did not give any interconnects. So routing is a stage where you give the interconnect, I mean to say that you give a logic interconnectivity according to the gate level netlist. So whatever nets, whatever interconnect information that you have got in the gate level netlist are physically routed, that means physically connected from one logic to other logic. So this is about the physical designing stage, and parallelly there are some other operations happening at this each and every stage. So we at the power planning stage, as I told you, we need to do some power manipulations for the circuitry. So that power manipulations are nothing but we create some power rings. So there might be some IPs like macros. Macro is nothing but a implemented logic or a pre-designed logic. We provide power rings for that modules if they are coming in my netlist, and some stripes for the gates, whatever are coming and sitting in the placement stage. So with the placement stage, a parallel operation of optimization also happens. So that is again like you are reducing the timing, power and area. So basically if you are considering an integrated circuit, you need to bother only about 3 parameters, that is the timing, power and area. So at every stage, parallelly from placement, an optimization stage is introduced where we do some manipulations to optimize these 3 parameters. So this completely is a physical design flow. So we are introducing that module also for the internships, and this is basically done in a tool called Innovus in Cadence. And yeah, so is it clear till now? So if I get any responses so that I can move forward with the other session.
Yeah, ma'am. Continue.
Oh, okay. So now I have a physically implemented gate level netlist or physically implemented design. Now, while doing interconnectivity or while it is doing routing, it is doing clock propagation, it has connected the gates, it has connected the logic in a proper way or not. So I mean to say the physical connectivity of the circuitry is tested in physical verification stage. So this is similar to the physical verification stage in the analog also. There you particularly do the verification for a particular cell, but here you do this process completely for the complete circuitry, like the complete module or the complete integrated circuit at a time. So basically we check for some checks like DRCs, LVS, ERCs, electrical rule checks, and the XOR checks. So like the shorts, opens, like the metal spacing issues, and when it is physically implemented, the routes are shorted or it is not connected properly, and that particular issues will be done at this physical verification stage. So this is again done in a tool called the Calibre, which is a mentor graphics tool. So in the Innovus tool also, we can implement this process of physical like the physical verification, but it will not show the accurate results. So we prefer another tool for physical verification if it is done in the Innovus. Also, like the physical design is implemented in Innovus tool, that is the Cadence tool for physical design. We do the Calibre process for physical verification. Now, I have checked the physical connectivity in the physical verification stage. Now,
What for we use encounter, madam?
sorry?
Tool encounter, what for we use?
Okay, so we encounter is basically the previous version of Innovus. So it is also done for the like used for the implementation of physical design itself. So the newer version of encounter tool is Innovus.
Okay, madam.
Okay. Now, next we enter into a stage called design for manufacturability. Once the design is physically implemented, we have done physical verification. We have checked for the metal issues, is the connectivity proper or not. Now, can I send it to the manufacturing stage? So I should make sure things here itself, because once going to fab, we can't modify the things, whatever it has connected, right? So we need to check the things once the post routing or post verification of physical
Madam,
verification is
sorry
done.
to disturb you.
Yeah.
Sorry to disturb you.
Okay.
I need a clarity regarding XR test and antenna. Some verification test you told, no? Can you give me clear explanation about that at least? In physical verification, you mentioned
Okay.
XR test and antenna something.
Okay.
Can you be little bit louder? It is not audible, Lahari.
Yeah, actually, I would like to know what it is about antenna checks and XR tests.
So antenna checks is basically like there will be a ratio defined for the for the antenna violations, like when a gate that is nothing but when a logic gate is connected to a metal, with how much distance it can connect, or with how much metal length it can connect to that particular gate. If it is using more metal length to connect to that particular gate, it will lead to an antenna violation. So that particular checks are called antenna checks, and XOR exclusive OR checks are one of the type of physical verification where you implement the logic circuitry with the help of some or inputs, like you introduce some XOR rules to implement to implement the circuitry in the verification stage. You give some XOR rules. It is also one style of verification actually. So if you have registered for this PD course, I can show it in the tool. So these are some like tool oriented concepts where you pass some files as an input, like to DRC. If you want, you will pass some minimal spacing rule deck, LVS layout versus schematic rule deck, electrical rule deck, and some XOR rule decks for a particular logic, and antenna rule decks. According to that rules what you have defined in that particular file, the checks are performed and you will get a output. So is it clear?
Yeah, okay, ma'am.
Okay.
What is ESD and IO rules?
So when you are doing some power planning, ESD is nothing but electrostatic distortion or electrostatic discharge of like if there are if you have done some power planning and you have passed some power rail where due to some issues, or due to some noise, or due to some jitter, or due to the input voltage that you have triggered at the input, that charges are flowing in a particular way that is causing the damage of my cell. That means wherever it is connected, wherever the power cell is connected to my gate, whatever input voltage you are passing through that particular net or the interconnect is causing some issue to my gate. So that checks are particularly checked in ESD, that is electrostatic discharge, where you are checking for the discharge of the voltage and the IO rules that is coming from the input voltage or not. So is it clear?
Yes, yes.
Yeah.
What is IO rules? Input output.
So okay, now you have some input and output pins in the gate level netlist. So you need to place that input and output pins with some spacings. Like it might be like it defined in the rule deck. According to the rule deck, we have specified as an input. It need to specify it need to be placed with some minimum spacing rules. So if it is failing that, we get an IO rule violation. So if it is not placed, the gate level inputs outputs are not placed according to the rules, we get such IO rules violations.
So just to add on here, physical verification will be done after the physical design process in the ASIC flow. And the rule deck, whatever some of these we have listed, right? The rule deck will be coming from the chip manufacturer. Okay, they will give DRC, LVS, right? All these, the details they will be providing. And there are specific tools per se. For example, in the industry, Mentor Graphics, Caliber, right? Caliber or Calibri. This is what is used as a sign-off tool. We call that as a sign-off tool, which takes this the rule deck and it applies on the ASIC database, which is physical design done. Right, so and then it will check for all these. So basically, all these rules, right? These are all electrical, characteristics, and during the manufacturing, what are the things they will be considering, right? All these, they would have put certain constraints, right? So those are the ones which will be fed as inputs for the database, ASIC database, which is designed. Okay, so each of these, that's a physical verification itself is a separate track, separate tool, and it will take this rule deck and then run on it. Any violations, it will show as violation, and then you will have to go and then see whether it could be waived or whether it's serious that it has to be fixed. Those kind of things. So they're all loaded. Each of these sentences are loaded. For example, ESD or IOs. There are a lot of IOs in ASIC, and each of these you need to look at those guidelines and the spacing, whatever. ESD, there's electrostatic discharge, so the static discharge, right? So even we also, human body carries the static charges, right? So the what level of it will not which it can tolerate or which can withstand, and which will be intolerant or which will cause damage to the circuit. So those are the things, actually, integrities if you get into. So otherwise it's the rule deck, what will be coming from the manufacturer. So that way it's a high level, but when we can deal with this, when we get into the physical design and the last part, physical verification, one session we will take for in the physical design session, actually. So maybe you can move on.
Sign off and tape out is same, sir?
Yeah, so the sign off or the tape out, yes, that is the last part. Yes.
Hello, sir and madam.
Yeah, go ahead. Go ahead.
Yeah. Hello, sir.
One of you. Yeah.
I just wanted to ask that this static timing analysis, is it necessary for sequential circuits, or is it to be performed on a pure computational circuit also?
Okay, so just let me ask you a question. What is combinatorial circuit?
No, sir. No, sir. I just wanted to ask. I am asking that this
static
timing analysis.
No. I am asking, like, have an understanding of combinator. Combinator circuit is what? It contains basic gates. Correct? Now,
Yes,
where you don't have flip-flops, you don't have the clocking, you don't have sequential circuits, in other words, which is having memory. Correct? Now,
Yes,
when
sir.
you are performing static timing analysis for combinatorial circuit, what does it mean? Now you are giving inputs and you are getting outputs. Outputs are coming after the delay of the combinatorial circuits, correct? So,
Yes, sir.
now to give an example, so you have 2 input AND gate. The AND gate delay, propagation delay is, let us say, 2 nanosecond. So A and B inputs will be passed to the Y output after 2 nanosecond. Okay, now there may be multiple stages of AND gate, OR gate, and then, so basically when you're doing timing analysis of a combinatorial circuit alone, so some of you mentioned multiplier. So you have built a multiple stage multiplier where the input, whatever you give, will be passed to the output after the propagation delay of all the stages of this multiplier. You agree?
Yes, yes, sir.
That is combinatorial circuit. Now, performing ST and combinatorial circuit is, you don't have much control because the delay is fixed, and maybe the line delays, maybe post layout delay, when you take some wire delays, maybe some considerations. Otherwise, there is nothing much to be analyzed only for combinatorial circuits. That is one thing. Second thing is, any device will be having both combinatorial and sequential circuit. Okay, so that is flip-flops in combination with the gates. You will see all these when you get into STA. And sequential circuits, you are giving reference clock, and then you are dividing the whole circuit into multiple timing arcs with respect to clock, right? You will analyze all the timings. That's what the static timing analysis tool does. Okay.
Yes, sir. Thank you, sir.
Yeah.
Okay.
Yeah, go ahead, Shravanti. Next.
So at this particular DFM stage, we check whatever physical connectivity it has done without an error free is ready for the manufacturing process or not. So in this particular stage, some extra efficiency is added to the design. It might be in the form of gates, so that the yield is more. I mean to say, the fabricated output we will be getting, the performance is more. So an extra efficiency is added in the form of metals or gates, so that the performance of the circuitry is more. This basically is again segregated into some of the corrections. So one of the correction is optimal proximity correction. So whatever routing it has done, whatever interconnectivity it has done between the logic is edge, I mean to say, with the help of metals, is the metal edges proper or not. It should be in a uniform way. The metal edges should be in a uniform way. There should be no distortion in a connectivity of the logic, or there should be no distortion in the metal with whatever it has got connected. So it checks wherever that metal edges are distorted, and some extra efficiency for that metal is added, so that the metal uniformly connects with the logic. So this particular correction is done at the OPC stage. So one more example I can address is when a circuit is connected logically, it will use multiple metals. So when it has to jump from one metal to other metal, for the logical connectivity, when it has to jump from one metal to other metal, it has to connect through a common component between the metals. That common component is nothing but a via. So when you come to the lower technologies, this via cells will not be detected by the manufacturing tool or the fabrication tool. So what they do at this optimal proximity correction stage is, they add some extra vias. That means the extra via cells wherever that connectivity of the metal has to be done, so that that connection will be detected properly with the help of multiple vias, and it will be fabricated, and we will not be having any issues. So these two are the examples of optimal proximity correction, and the other is called double patterning or dual patterning.
Madam, excuse me, what is VR cells?
So VR cell is nothing but like when you physically implemented a logic, there will be no single metal. I mean to say, to interconnect the logic, we use metals. So there will be no two type. I mean to two same type of metals. We have different types of metals to interconnect the logics. So when you need to jump from one metal to other metal, that means you need to connect from metal one. So if suppose there are five metals, so I need to connect metal one and metal two. So from metal one to metal two, if I need to jump, I need to have some common medium. So that common medium is called as via. So that via cell provides the connectivity between two different metals. Is it clear?
Yes, madam.
Okay, so one of the other manufacturability check is dual patterning. So this is basically for the lower technologies, that means like below 14 nanometer technologies. So whatever metal layers or the interconnects you are using for the implementation, that metal width or the spacing will be reducing when you go to the lower technologies. That means it will be very less, such that the fabrication tool cannot detect that metal spacing or metal width. So if you know the fabrication of an like a CMOS or anything, any circuit, where the process of masking is done, it is under the process of photolithography, where the masking of the metals or the inputs or the outputs is done with a silicon layer. So this at this particular stage, because it is not able to detect the metals once we are entering into the lower technologies, a mask layer is surrounded to that particular metal, so that it can detect that metal spacing and metal connectivity when we go to the I mean to say the fabrication stage. So this helps in two formats. So where we can we can detect less sort of issues in the physical verification stage also, if you are following this dual patterning. So to avoid shorts and some opens, this particularly helps. So once this is done, if you are following, like if you are facing issues regarding the DRC again, you need to go back again to the DRC stage and give this specification of the metal width, and so that at the fabrication stage for that particular metals, they will apply this double patterning or the masking of the metal layers. So this is what is double patterning. Now, so
Excuse me, madam.
yeah.
Madam, we'll be saying metal 1, metal 2, like metal 5 up to metal 5 you told.
Yeah.
It's a general question. In what way these metals are different?
So, Larry, just I want, sorry for intervention here. So there's more of physical design related topic. So let us just discuss in the physical design classes. So here, the last stage in the ASIC, this thing is what we are discussing, and then further synthesis is our main this thing after giving introduction to it. So offline, we will answer. You can WhatsApp to Shravanti, Larry. So already we are 8 o'clock now. So let us move further. Okay. So because that itself is a different topic altogether. Okay. Sorry for cutting you off. So we will discuss offline. Okay.
It's okay. It's okay.
Yeah. Now it is tested manufacturally, like it is tested like it will be ready for manufacturing or not. Now if you are not facing any issues, so we need to write out a GDS file from the tool, so that this graphical format of file is sent to the fabrication and the circuitry is implemented on the chip. So this is not a human readable format, it is a tool understandable format, where the physical information, the information of the circuitry, once everything is tested and once everything is error free, then it is implemented in this graphical design schematic and sent to the fabrication. So one query was arise, like what is tape out and sign off. So sign off is nothing but where you are performing checks. So wherever you are performing checks, like the timing issues and the DRC issues and the physical verification issues, is called a sign off stage. And the tape out stage is nothing but your complete design is sent to the fabrication industry for the manufacturing. So testing stage comes under the sign off stage, and the complete circuitry you have implemented and you are giving to a manufacturer is called tape out. So this is the complete flow of ASIC. So any queries regarding this? The complete flow? Okay. So we'll move on to the synthesis process. So in a descriptive way, what is synthesis process is, again, the synthesis process is the conversion of RTL code to a gate level netlist. So as I discussed, we give an input as an RTL code. It might be a Verilog or it might be a VHDL code. We give that input to a synthesis tool, and what we get as an output is a netlist file. So to convert this process, I mean to say, to convert this gate level netlist from the RTL, it is basically comprising of 3 steps. So the first step is translation, and the second step is mapping, and the third step is logic optimization. So once your RTL is given as an input to the synthesis tool, it will not convert directly into a gate. It will follow some steps and some stages to convert it into a gate level netlist. So the first stage it follows is a translation stage, where your RTL code is converted into a Boolean expression format. So we convert the complete RTL code into a Boolean expression format, and that will be in the form of basic logic gates, and this is also called as unmapped format. So it is not mapped to any technology. So it is not mapped to any technology, like you want to implement it into some 45 nanometer technology. This gates will not be mapped for the 45 nanometer technology. It will just get converted into some Boolean expression format or some logic according to the Karnaugh maps algorithm, which is already automated in the tool. So translation is a step where the RTL code is converted into a Boolean expression format. So now, as I told you, this gates which are converted or translated should be mapped to the particular technology input. So if you give an input of a 45 nanometer library where all the cells are present, it will convert that into a technology dependent 45 nanometer gate level netlist. So in the mapping stage, whatever unmapped format or whatever generic conversion of gates that has been done in translation is mapped to the library gates. So library is nothing but a file where you comprise, where you have some set of gates, and that gates are mapped to the unmapped format. So this you can see it in the tool process when I do the execution again. So, and next is optimization. As I told you, as a backend engineer, the 3 parameters we need to take care of is basically timing, power, and area. So we give some constraint files. So synopsis design constraint file, where it will give some optimization results in the power, performance, that is nothing but the timing, and the area. So using this file called SDC file, it does this optimization and gives some optimized gate level netlist in terms of the power, performance, and area. So these are basically the 3 steps while it is doing the process of conversion into gate level netlist. So you can write out the gate level netlist at the mapping stage also, but it will not be optimized. The power might be varying, the timing might be failing, and the performance or the area occupied by the gates will be more. But if you write out an optimized gate level netlist, it will give you a reduced gate count, and it will be optimized in power and timing also. So you can write out a gate level netlist at both stages. So these are basically 3 steps in the process of synthesis. So finally, once the synthesis is done, what we are achieving is to generate a gate level netlist, obviously. So RTL is getting converted to a gate level netlist, and we are inserting some clock gates for power optimization. So how this happens is, as we discussed in the module or in the gate level netlist, most of the cells will be sequential cells. So there might be some circuitry where all the sequential cells should not be functioning at some time. I mean to say, some sequential cells or group of cells should have to do the propagation of clock at particular time, and some other group of cells should be doing the propagation of clock at the other time. So when you are oning and offing the propagation of clock, that means indirectly you are reducing the switching activity of the clock. That means the switching activity is again constrained for the power. So the switching power indirectly you are saving by inserting the clock gating cells. So in one of the goal of synthesis is also you are introducing the clock gates in the gate level netlist, where you can optimize the power. So logic optimization for area. So once you give an SDC file, it will optimize the gate size also, and indirectly you are optimizing the area occupied by that gates. And inserting DFT structures. So the total design or the total integrated circuit is basically implemented in two types. One is functional mode and one is scan mode. According to the application point of view, the front end engineer will be defining a logic where you can introduce the scanning cells which are ready for the manufacturability or the productivity at this stage itself. So when you are introducing that scan cells to check the controllability and observability of the circuit, you can use that scan mode, that is nothing but DFT mode, and you can introduce that scan logic at this stage itself. So when you are implementing the logic in scan mode itself, you need to introduce this DFT logic. So once after synthesis is done, obviously logic equivalence check is done between RTL and Netlist, where you are checking my logic of RTL and logic of Netlist is same or not. So the advantages of doing synthesis is basically abstraction. That means you are completely segregating the logic, the top level logic, into some simplex gates like to basic AND gate, NOR gate, and you are dragging down to that particular parameter where the logic is defined at a basic level.